Like this? Yeah? Great. Perfect. Okay, very good. So let me start. So the title of my talk on the program is actually slightly different. So if you came here to, or we're hoping to hear me speak about extragalactic magnetic fields and starburst galaxies correlated with ultra-energy cosmic rays, then sorry to disappoint you, but feel free to catch me later on in the conference if you have any questions about that. So I asked the organizers to switch topics, and luckily they agreed. So I'm now, what I'm going to talk about is fits to the ultra-energy cosmic ray spectrum and composition of both the Pierre Auger Observatory and telescope array. And yeah, little spoiler alert, this only works if you add a local source of ultra-energy cosmic rays, additional local source of ultra-energy cosmic rays in the northern hemisphere. So this work is mostly done by Pavlo Plotko. He's a PhD student at DAISY that I'm supervising. And so let's get started with a bit of introduction. So of course we all know that the main players in ultra-energy cosmic ray physics are the telescope array and the Pierre Auger Observatory, where we have telescope array in the northern hemisphere and the Pierre Auger in the southern hemisphere. So they have different fields of view. And they also see different spectra. So these are the two, the brown spectrum here is what telescope array sees, and the black one what the Pierre Auger Observatory sees. Now there's clear differences here, but what this plot does not show are the systematic uncertainties of the, which are 14% for Auger and 21% for telescope array. So what you can do is just shift these two so that they fall on top of each other within their systematic uncertainties, which is what's done here. So both of these and the energies of them both rescaled by 4.5%. And then you have a beautiful agreement at lower energies below the angle and even up to higher energies, except for at the highest energies, where there is still a difference there between telescope array and Pierre Auger Observatory in the energy spectrum. So the question that we are trying to answer is if we can explain this with an astrophysical origin. So basically, this is our goal, trying to get the Pierre Auger Observatory and telescope array together, which has been, I think, a challenge for many decades already in all kinds of different ways. But at least looking at the spectrum, this is now what we're trying to do as a theory group that is not in either of the two collaborations. So yeah, we're not going to look at differences between the different detectors. We're just going to treat them equally and see if we can explain especially this difference in the spectrum here. Now, so what we're the idea in this case is that we're trying to explain these differences by adding a local source in the north. And of course, these two have different fields of view. We see, so if we add a local source in the north, it will only be observable by telescope array and not by Auger. So you could expect a difference like this to come from that idea. So what this would look like in terms of the spectrum is that you have a isotropic source spectrum that is visible by both. So faraway sources get deflected in magnetic fields, and you see the general spectrum both in the northern and southern hemisphere. So in this case, you get the sketch of this green line here. This is visible by both, which gives you the same spectrum in the north and the south. And then if you have a local source in the north only visible by TA, then you get additionally this red line here, which is then detected by a telescope array alone. And what is nice to speculate on here, this is just speculation, but what is interesting to see here is that this the new access, as was reported by telescope array at the previous ICRC, starts at this energy range, which is exactly the same energy where this deviation in the spectrum between telescope array and Auger starts. So yeah, you could speculate that this is related to this additional local source in the northern hemisphere. So we're not going to look at arrival direction data in this study. We're just looking at spectrum and composition. But it's of course nice to speculate in this direction. And the hotspot observed by telescope array, that part of the sky is actually about 1 energy bin at higher energies. So this is, but of course also still okay, at least for these kind of studies. So for those of you who have seen me talk before, normally I have a slide here that says we're doing these kind of propagations with Sierra Propa. In this case, we use a different code. We use Prince, which is a code developed at DAISY, also for ultra-high energy cosmic ray propagation. So it's also publicly available. It's pure Python code, which uses matrix algorithms to do this kind of 1D simulations in a very fast way, meaning that you can scan over parameter range, large parameter ranges quite easily. And so this is mostly developed by Jonas Heinze and published in 2019. Yeah, it's a bit slow. Okay. So oops, wrong direction. So what we do for source, ultra-energy cosmic ray source assumptions, so this is a bit a technical slide, but the main message is that we use the standard methods that everybody is using. So you can also see, so check Antonio Condorelli's talk from yesterday. He uses the same assumptions here. And this is also the same assumptions that were used in the Auger combined fit paper and in several other papers after that. So we have just a simple power law spectrum at the sources with rigidity-dependent cutoffs, with a specific source evolution, and we have 5 injected elements at the sources, and then yeah, we run these source assumptions through the propagation simulations to see what we get at Earth, and we have several fit parameters to make this work. Which is one which corresponds to the source evolution, the spectral index at the sources, the maximum rigidity at the sources, and the fractions of the different elements that are emitted by the sources. And of course, we have several hadronic interaction models and uncertainties on composition and so on. So basically, to deal with this, we do this whole setup for all 3 hadronic interaction models. So let me show you the results of for the best fit case, at least. So on the left-hand side, these are the spectrum and composition that we get if we do not include a local source. So this is very similar to the best fit results that OJ found and several other papers found as well. So we can nicely produce the OJ spectrum and OJ composition, but of course this telescope array spectrum with the highest energies is not reproduced in this way. So here we see the spectrum, how it's reproduced, but yeah, I mean there are differences in the measurements, so of course we cannot reproduce. The FITS prefers in this case the PRJ observatory results, just because the OJ results have larger statistics, smaller error bars. So that's why this basically reproduces really well the OJ results, but unfortunately not the telescope array results. So if we now add a local source, and here then we can get still the same line, the same black line for the full spectrum and for OJ. But what we expect for telescope array is then this brown line, which is a nice fit of the telescope array spectrum then as well. So yeah, this means that we, by adding a local source to this only visible by telescope array, we can explain both OJ spectrum, telescope array spectrum, mass composition measurements, all at the same time. So what we do for this local source is we assume that at least in the range where it's dominant, where it's interesting, this local source produces one specific mass group. So if you look at the energy range where this local source becomes dominant, then this is here in this energy range where you really add the highest energies for the mass composition. So we don't have much mass composition data there. It's also only dominant in relatively small energy range. So to add more than one mass group for source just gives you more free parameters to fit, which doesn't really make sense in the end. So we have one mass group which is dominant for this local source. And in this case, the best fit is the silicon mass group, but other mass groups you can also get decent fits. And in this case, the distance, you can also, doing these fits, you have several parameters for this local source, so that the maximum energy of the local source, the distance of this local source, and the spectral index of this local source, so you get, and the luminosity of the local source as well. So you cannot get all these kind of information out of this fit. So we see a distance that should be smaller than about 22 megaparsec, and maximum rigidity for this local source about 1.3 times 10 to the 18 volts, relatively low, but it's because we have a relatively heavy mass group here. So how does this? So what about the distance in this case? So here we have the distance of this local source versus the different mass groups. So you see that the heavier the mass group, the larger the distance you need. And for if you assume iron, we can still have within 1 sigma, so the darkest error bars are for the 1 sigma scenarios. We can get distances up to 100 megaparsec. But once you go to lighter mass groups, you get need a closer source. And protons and helium sources are actually excluded within at least 1 sigma. So then we go to the conclusions here. So these differences in the ultraviolet cosmic ray spectrum between OJ and GA can be explained by adding a dominant local source in the northern hemisphere. There's actually a 5.6 sigma difference if you compare this strictly with only an isotropic distribution, so that OJ and telescope array would see the same flux. In the best fit case, we have sources that should be smaller, should be nearer by than 23 megaparsec, but this also depends on the actual mass group interaction, so freedom you're playing around with that.